Hey folks, I decided that I'd try and give you a couple more examples about probabilities since it is a really important area and I may have undersold its usefulness before. So here we go. To begin with, let's pick something that's actually a little bit more concrete. This is my little dog. She's a Jack Russell Terrier. Her name is Lucy. And I wanted to see, all right, well, given that we know that she's 10 years old, what is the likelihood that she will, die in the near future? I don't want her to die, obviously, but let's see. So the average lifespan of a Jack Russell is 13 to 16 years, and you can look that up on Google. Now, unfortunately, a standard deviation isn't given with this calculation, but you can use something called the range rule, which is a very rough estimate of the standard deviation. And this only works because 95% of the scores fall within 2 standard deviations of the mean. And you'll note that we're assuming that the distribution is normally distributed. So in order to calculate this, and I'm not going to ask you this on the exam, this is just a way for me to sort of try and get an estimate of the standard deviation while we're doing this example. You take the maximum minus the minimum, divide by 4. So in our case, we have a maximum age of 16 years minus 13 years divided by 4, which gives us approximately 0.75 years. Now that we have that, we have our x, which is Lucy, she's 10 years old, minus the average, which is 14.5, which is the average of 16 and 13, divided by 0.75, and we get a z-score of negative 0.6. What can we do with that? Well, we can basically say, all right, well, here is the normal distribution of scores centered around 14.5 years old. We can then say, all right, well, since we know that the standard deviation is 0.75, we can add that to get all the remaining values. We can also get the z-scores that are associated with them. We know that Lucy is 10 years old and has a z-score of negative 6. She is so far off this distribution that the odds of her actually dying of old age at the present age is about 1 in a billion, which is awesome. However, you'll see that as dogs start to reach the age of 12 and a quarter, 13, 13 and 3/4, and so on and so forth, the risk of death increases until you get to about the average age of death, which is 14.5. Another way of saying this would be, it would be 97.5% likely that my dog will reach the age of 13, about 84% likely that she'll reach the age of 13 and 3/4, 50% likely that she'll reach 14.5, 16% likely that she'll reach 15.25, and only 2.5% likely that she'll reach the age of 16. So she's got some time yet, which is wonderful, because she's a lovely little thing. The other thing that we can look at is the binomial distribution. So let's assume that we're interested in studying left-handed people, because left-handed people are an understudied group of people. We know that most psychology studies tend to eliminate lefties from their studies, since left-handed people tend to have, well, not only responses that would be dominated by the other hand, and so reaction times might not be meaningful. But you also find that if you're doing brain studies, things that are typically left lateralized in people who are right-handed tend to be equally distributed across people who are left-handed. So you might find activations in a group of left-handed people that were not as meaningful as you thought they were if you were comparing them to the right-handed people. So let's say that we wanted to come up with a study that just looked at left-handed people, but we weren't actually recruiting for left-handed people. We were just going to sample randomly a group of 100 people. What would be the odds of getting exactly 16 people in this who were left-handed in this sample? Basing this off the odds that, about 10% of the population is left-handed and approximately 90% of the population is right-handed, we can then fill in the formulas. We can use the binomial formula. So Pn is the probability of selecting a left-handed person in our example, and we have 0.1, because we said 10% of the population is left-handed, multiplied by 100, because we're selecting 100 people. That's about 10. Qn is the probability of selecting a right-handed person, and in our case we have 0.9 times 100 is 90. Both the n's are greater or equal to 10, therefore we can use the normal approximation to the binomial formula, which we will get to in just a second, but it involves these values here. So the mean in the normal approximation to the binomial is just Pn, which is 10, and the standard deviation is approximated by taking the square root of the total of n multiplied by p, which is 0.1, multiplied by q, which is 0.9. And here you can see the normal approximation to the binomial here. So, in our case, we can substitute in our values, and remember that we are trying to find exactly 16 lefties if you sample a group of 100 people. That means since you can't exactly choose the probability of 16, it's an exact point, you can't get a probability for an exact point, you need to use real limits to go slightly above and slightly below in order to capture that probability space, because you're talking about an area of a distribution. So in order to do that, we have to say, all right, well, go half a unit up, 16.5 minus 10, and 10 again is the actual probability of the event happening. It's the average. Minus, or divided by, in this case, the standard deviation of 3, which is, again, NPQ square root. And that gives us a z-score of 2.166 repeating. Then we take the probability space slightly below the value that we're looking for, 16, 15.5 minus 10 divided by 3, and that gives us a z-score of 1.833 repeating. Now we can take these values and we can plug them into our z table, and we find that the probabilities are associated with these values. So a probability that's associated with a z of 2.16 in the tail is 0.0154, and similarly the probability that's associated in the tail with a z value of 1.833 repeating is 0.0336. So now, in order to actually find the probability with the area that we are looking for, we have to subtract these two values. This is quite simple, similar to the value, or the idea that we were looking at in class, where we were looking at the distance from the mean to a certain value. But in this case, we're actually looking at the distance between two areas that are surrounding a value that we're trying to look at using real limits. So, therefore, that's what the sign means. The probability associated with selecting exactly 16 left-handed people from 100 random samples is 0.0336 minus 0.0154. So you get about 0.01796, or about